Picture an ocean of darkness so vast it defies comprehension, stretching billions of light years across, where galaxies are mere specks, lost in an endless sea of nothing. This isn't science fiction, it's the reality of void superclusters, the universe's most desolate frontiers. These aren't just empty patches of space, they're cosmic voids so colossal they reshape our understanding of reality itself. Imagine standing at the edge of one, staring into an abyss where the nearest galaxy is so far away, its light would take millions of years to reach you. That's the scale we're dealing with, a silence so profound it echoes across eternity. What makes these voids even more mind-bending, they're not random. These are carefully sculpted absences shaped by forces we're only beginning to unravel. Scientists call them void superclusters, and they're more than just empty space, they're the fingerprints of the universe's hidden architecture. Think of them as the negative space in a cosmic painting, where what's not there tells us just as much as what is. These voids hold clues to dark energy, the fate of the universe, and even the origins of everything we know. And yet, most of us have never even heard of them. That's why we're diving into this mystery today. Because beyond the stars, beyond the galaxies, there's a story written in emptiness, one that challenges everything we thought we knew about space, time, and our place in the cosmos. This isn't just a tour of the universe's emptiest places. It's a journey to the edge of understanding. By the end, you'll see the night sky differently. Not just as a tapestry of light, but as a map of the unimaginable voids lurking between it all. So let's start where the universe holds its deepest secrets, in the nothingness that shapes everything. Void superclusters are the universe's grandest illusions. What looks like empty space is actually a carefully arranged cosmic stage. Picture a sponge on a colossal scale. The holes aren't random gaps but vast, sculpted voids bordered by dense threads of galaxies, like webs of light stitching the darkness together. These structures are so immense that a single void can span hundreds of millions of light years, with galaxies huddled along its edges like shy spectators avoiding the center. But here's what sets them apart from ordinary cosmic voids, where typical voids are just pockets of nothingness. Void superclusters are part of an intricate hierarchy, the largest known structures in existence, shaped by forces that defy intuition. How do these colossal absences form? One leading theory points to the early universe, where tiny fluctuations in density smaller than an atom snowballed over billions of years. Regions with slightly less matter expanded faster, pushed outward by dark energy's relentless push, while gravity pulled galaxies into the filaments we see today. It's like watching dough rise. The emptier stretches grow while the denser clumps knot together. But the real twist, these voids aren't truly empty. They're peppered with rogue galaxies and dark matter, faint echoes of the universe's scaffolding. What fascinates scientists most is how these voids warp reality itself. Light crossing a void supercluster stretches, its wavelength tugged by the void's gravitational pull, a phenomenon called the integrated Sachs-Wolfe effect. Even time moves differently here, warped by the absence of mass. These voids aren't passive blanks, they're active players in cosmic evolution, their growth accelerating as dark energy tears the universe apart. To study them is to study the fate of everything. And yet, for all their grandeur, they remain nearly invisible, hiding in plain sight between the stars we know. The story of how we uncovered these cosmic voids reads like a detective novel, a slow unraveling of the universe's best-kept secret. It began in the late 1970s, when astronomers first noticed strange gaps in galaxy surveys, regions where the night sky seemed oddly dark. At first, they dismissed them as observational errors or patches of dust blocking our view. But as telescopes grew sharper, a pattern emerged. The universe wasn't uniformly sprinkled with galaxies. Instead, vast empty regions dotted the cosmic landscape like bubbles in foam. One of the pioneers of this revelation was astronomer Stephen Gregory, who in 1978 mapped out the Coma supercluster and stumbled upon a stunning emptiness beside it, a void so large it defied explanation. Around the same time, his colleague Laura Kretschmer was studying the Boötes Void, a staggering expanse spanning 330 million light-years, containing barely a handful of galaxies. These discoveries shattered the old assumption that matter was evenly distributed, revealing a universe more structured and more mysterious than anyone had imagined. But the real game-changer came with projects like the Sloan Digital Sky Survey, launched in 2000. For the first time, astronomers could map millions of galaxies in unprecedented detail, exposing the full skeleton of the cosmos. What emerged wasn't just a few isolated voids, but an intricate cosmic web, with voids making up nearly 80% of the universe's volume. Scientists like J. Richard Gott and Mario Jurek used this data to show how these voids aren't accidents but fundamental features, shaped by the same forces that birthed galaxies. The irony, early 20th century astronomers like Carl Seyfert had actually glimpsed hints of voids in their plates, but lacked the tools to recognize them for what they were. It took decades of technological leaps, from photographic plates to digital sky surveys, to reveal the true scale of these absences. Today, missions like ESA's Euclid telescope are probing deeper, using voids as laboratories to test dark energy and cosmic expansion. What began as curious blank spots on a map are now keys to understanding everything from gravity's grip to the universe's ultimate fate. And to think, it all started with a few astronomers asking, why is there nothing here? To grasp the sheer scale of Void Superclusters, let's start with a cosmic perspective you already know, the Milky Way. Our galaxy stretches 100,000 light-years from end to end, a distance so vast it would take a beam of light 100 millennia to cross it. Now imagine that galaxy as a single grain of sand on a beach. Even at that scale, the Void Superclusters we're discussing would be like empty stretches of ocean so wide you couldn't see the other side. Take the Boötes Void, one of the most famous of these cosmic deserts. At 330 million light-years across, it's so large that if you placed the Milky Way inside it, you'd need to travel the equivalent of 3,000 Milky Ways laid end to end just to reach the nearest wall of galaxies. To put that in earthly terms, it's like standing in the middle of an empty Sahara so enormous, the nearest oasis would be farther than the distance from Earth to Pluto, and then multiplied by 10,000. But even Boötes pales in comparison to the giant void superclusters we've mapped more recently. The Eridanus Supervoid, for instance, spans an almost unimaginable 1 billion light-years. That's a hole in the cosmos so big, it could swallow our entire local group of galaxies, including Andromeda and dozens of smaller neighbors, and still have room to spare. If you tried to fly across it at the speed of light, you'd spend longer traversing that emptiness than multicellular life has existed on Earth. Here's what makes these voids even more staggering. They're not just empty spheres. Their shapes are intricate, almost fractal-like, with smaller voids nesting inside larger ones like bubbles within bubbles. The filaments of galaxies that outline them aren't neat borders but tangled cosmic rivers, weaving around these absences in a dance that's lasted billions of years. And the scariest part, we're likely underestimating their true scale. Every time our telescopes peer deeper, we find voids that push the limits of what we thought possible structures so vast they redefine the word empty. Yet for all their immensity, these voids aren't static, they're growing. Dark energy is stretching them wider every second, accelerating their expansion in a way that will one day make the universe's emptiness its most dominant feature. That's the paradox of these cosmic giants. The more we learn about them, the more they remind us how small we truly are in a universe where nothingness is the rule, not the exception. The Boötes Void isn't just an empty patch of space, it's a cosmic anomaly so puzzling. Astronomers initially doubted it could exist. Stretching 330 million light-years across, this colossal absence is often called the Great Nothing, a title that barely captures its strangeness. To put that scale into perspective, if our Milky Way were a single house, the Boötes Void would be an empty continent roughly the size of Australia. And yet, despite its staggering size, this void contains fewer than 60 galaxies. In a region where scientists would expect thousands, that number is so low it's like finding a handful of pebbles scattered across an entire desert. What makes Boötes especially intriguing is how it defies expectations. Most cosmic voids have galaxies huddled along their edges, but Boötes flips the script. It's too empty, even by void standards. The few galaxies found inside it aren't clustered together but isolated, like lone travelers stranded in an endless wilderness. Some researchers believe these stragglers might be field galaxies, cosmic nomads that drifted into the void after being ejected from denser regions by gravitational interactions. Others speculate that the void's extreme emptiness could hint at unknown physics, perhaps even relics from the universe's earliest moments. Then there's the mystery of its shape. Unlike neatly spherical voids, Boötes is irregular, with jagged edges and filament-like tendrils of galaxies weaving around it almost as if something carved it out unevenly. One theory suggests it might be the result of multiple smaller voids merging over billions of years, like soap bubbles combining into one enormous cavity. Another, more radical idea proposes that Boötes could be evidence of a collision with a parallel universe, though this remains speculative. For astronomers, Boötes isn't just a curiosity, it's a laboratory. By studying how light from distant galaxies bends as it passes through the void, they've detected subtle clues about dark matter's distribution. The void's sheer size also makes it a prime testing ground for theories about dark energy, as its expansion rate could reveal how this mysterious force operates on the largest scales. And because Boötes is relatively close in cosmic terms, just 700 million light-years away, it's one of the few voids where we can study individual galaxies within it, offering snapshots of how galaxies behave when starved of cosmic neighbors. Yet the most haunting question remains: why is Boötes so empty? Even with our best simulations, replicating its vast, sparsely populated expanse has proven nearly impossible. Some scientists wonder if it's a statistical fluke, a 1 in a trillion chance in the cosmic lottery. Others argue it's a sign we're missing a fundamental piece of the puzzle. Either way, the Boötes Void stands as a humbling reminder that the universe reserves its deepest mysteries not in the brilliance of stars, but in the silence between them. To understand why void superclusters are so unimaginably empty, we need to rewind time, back to when the universe was just a seething soup of particles moments after the Big Bang. Tiny quantum fluctuations in this primordial chaos created microscopic differences in density, areas where matter was slightly more or less packed together. Over billions of years, gravity amplified these differences, pulling matter into dense knots that became galaxies, while the emptier regions stretched and grew. But here's the twist: it wasn't just gravity at work. Dark energy, that mysterious force accelerating the universe's expansion, played an equally crucial role. Picture it like a cosmic tug of war. Gravity pulls galaxies together, while dark energy pushes the emptiness between them apart. In void superclusters, dark energy won spectacularly. One leading theory suggests these voids grew so vast because of a runaway effect called gravitational repulsion. As matter clumped into galaxies and clusters, the emptier regions had less gravitational pull, meaning they expanded faster. This created a feedback loop. The more a void grew, the weaker its gravity became, allowing it to stretch even further. Imagine blowing up a balloon with weak spots. The thinner patches stretched the easiest, becoming enormous while the thicker areas stayed dense. That's essentially what happened on a cosmic scale, with void superclusters as the ultimate thin spots. Then there's the role of the early universe's matter distribution. Simulations show that if the initial density variations were just slightly different, voids might have remained small or never formed at all. It's like baking a cake with uneven batter. The air pockets or voids grow where the mixture is thinnest. Some scientists even speculate that certain voids might be primordial, their emptiness locked in place since the universe's first seconds, preserved like fossils in the cosmic web. But the real wild card is dark energy. As it accelerates the universe's expansion, voids act like its amplification chambers, their emptiness offering little resistance, allowing dark energy to stretch them faster than denser regions. This could explain why voids like Boötes are growing even emptier over time, their few remaining galaxies isolated like islands in an ever-widening sea. Yet mysteries remain. Why do some voids, like Boötes, defy expectations with their extreme emptiness? Could there be exotic physics at play, like quantum fluctuations frozen in time or undiscovered forces? Or is it simply a statistical fluke, a cosmic dice roll that left these regions unusually barren? The answers might lie in future telescopes probing the faint echoes of the early universe, searching for clues in the silence between the stars. One thing's certain, void superclusters aren't passive absences. They're dynamic, evolving landscapes, their emptiness a testament to the universe's most powerful forces we're only beginning to understand. Dark matter is the universe's hidden architect, an invisible force weaving the cosmic web into existence, including the vast, empty expanses of void superclusters. Though we can't see it directly, its gravitational pull is the sculptor behind the universe's grandest structures. Picture a spiderweb glistening with dew. The strands you see are galaxies, but the web itself, the delicate, anchoring framework, is dark matter. Without it, those colossal voids wouldn't just be emptier, they might not exist at all. Here's how it works. In the early universe, dark matter clumped together under gravity's pull, forming an intricate scaffold. Ordinary matter, the stuff of stars and galaxies, flowed along these invisible threads, pooling where the dark matter was densest, but the regions between. They became the voids, simulations like the Millennium Run, which mapped the evolution of billions of dark matter particles, revealed this process in stunning detail. The voids aren't accidents, they're the negative space left behind as matter drains into denser filaments, like water receding from bathtub walls. What's fascinating is how dark matter's distribution dictates a void's growth. In areas where dark matter is sparse, gravity's grip weakens, allowing space itself to stretch faster. This creates a feedback loop. The emptier a region becomes, the more dark energy accelerates its expansion, pushing galaxies even farther apart. It's why voids like Boötes aren't just empty, they're expanding emptiness, their borders thinning as dark matter's influence wanes. Yet dark matter's role isn't just about absence. Even in the deepest voids, traces of it linger, a faint gravitational echo. Some theories suggest these isolated dark matter halos could host failed galaxies, clumps of gas that never ignited into stars. Others propose that voids might contain rogue dark matter particles moving slower than their counterparts in denser regions, relics of the universe's earliest moments. The real breakthrough came when astronomers noticed something peculiar. The shapes of voids aren't random. Their edges align with dark matter filaments like fingerprints pressed into the cosmos. By studying these alignments, scientists can map dark matter's distribution indirectly, using voids as cosmic projection screens. When light from distant galaxies passes through a void, its path bends subtly, warped by the void's gravitational field, a phenomenon called weak gravitational lensing. These distortions reveal the void's true structure, hinting at the dark matter skeleton beneath. But the story doesn't end there. Dark matter's gravitational tug doesn't just shape voids, it dictates their destiny. As the universe expands, dark energy dominates, stretching voids faster than ever. Yet simulations suggest dark matter might one day fight back. In some models, the gravitational pull from surrounding filaments could slow a void's growth, even collapse it over trillions of years, folding emptiness back into the cosmic web. It's a reminder that void superclusters aren't static deserts, they're dynamic landscapes, shaped by an unseen hand. The irony, dark matter, which makes up 85% of the universe's mass, is most visible where it's least concentrated. In the voids, its absence speaks louder than its presence. By studying these empty regions, we're not just mapping nothingness, we're decoding the hidden language of the cosmos, written in gravity's silent whispers. If the cosmos were a city, void superclusters would be its abandoned districts sprawling, echoing expanses where the lights have all but vanished. Meanwhile, galaxy-rich superclusters like Laniakea would be the bustling downtown cores, alive with activity. The difference between them isn't just scale, it's a fundamental divide in how matter organizes itself across the universe. Take Laniakea, our home supercluster, a gravitational metropolis spanning 500 million light-years, with 100,000 galaxies swirling like commuters around a shared center. Now imagine the Boötes Void again, a region of similar size, but where you'd struggle to count more than a few dozen galaxies. That's the cosmic contrast we're talking about, one side teeming with stars, the other a near-perfect vacuum. The numbers alone are staggering. In a typical supercluster, galaxies pack together at densities up to 10,000 times higher than in voids. Picture the difference between a crowded stadium and a lone spectator sitting in an empty desert. But it's not just about raw counts, it's about structure. Superclusters like Laniakea form intricate webs, with galaxies streaming along filaments toward great attractors, massive gravitational anchors like the Norma cluster. These filaments are the cosmic highways, funneling galaxies into dense knots over billions of years. Voids, by contrast, are the absence of such order. Their few galaxies drift like lost ships, unmoored from the gravitational currents that shape busier regions. What's truly fascinating is how these extremes coexist. The same forces that carved out voids also built superclusters. Remember those tiny density fluctuations in the early universe? In overdense regions, gravity had more to work with, pulling matter into the dazzling structures we see today. In underdense areas, the opposite happened. Gravity's weaker grip let dark energy take over, stretching space into emptiness. It's like watching two siblings grow up in the same neighborhood. One becomes a magnet for opportunity, the other fades into isolation, shaped by the same environment but responding in wildly different ways. Yet even superclusters and voids share an underlying kinship. Both are part of the cosmic web, that grand tapestry where galaxies trace the outlines of both presence and absence. And just as voids aren't perfectly empty, superclusters aren't solid blocks of galaxies. Laniakea, for all its grandeur, is mostly empty space too, its galaxies clumped along delicate threads, with voids threaded between them like the gaps in lace. The difference is one of degree, not kind. This cosmic imbalance raises profound questions. Why did matter clump so unevenly? Could the universe have turned out differently, with a more even spread of galaxies? Simulations suggest the answer lies in those initial quantum fluctuations, a cosmic roll of the dice that set some regions on the path to richness, others to emptiness. And here's the twist: without voids, superclusters might not exist at all. The same expansion that stretched voids also compressed matter elsewhere, making the dense regions denser. The universe's emptiness, in other words, is what allows its brilliance to shine. So the next time you look up at the night sky, remember, the stars you see are the exception, not the rule. For every glowing point of light, there are volumes of darkness so vast they defy comprehension. The universe isn't just a collection of galaxies, it's a dialogue between fullness and absence, where the silence between the notes is as meaningful as the music itself. Deep in the cosmic microwave background, the afterglow of the Big Bang, there's a chilling anomaly, the cold spot. a patch of sky roughly 0.015 degrees wide, where temperatures dip mysteriously lower than the surrounding universe. At first glance, it might seem like a minor statistical blip, but this cold spot is anything but ordinary. Stretching over 1.8 billion light-years, it's a cosmic bruise so vast it could swallow thousands of Milky Ways. And the leading theory, it might be the shadow of a void supercluster, an emptiness so colossal it warps the very fabric of space-time. The cold spot was discovered in 2004 by NASA's Wilkinson Microwave Anisotropy Probe, a spacecraft designed to map the faint whispers of the early universe. Normally, the cosmic microwave background is remarkably uniform, with temperature variations no greater than 100,000th of a degree, but the cold spot defies that pattern. It's colder by about 70 microkelvins, a tiny number on paper, but a glaring outlier in a sea of near-perfect equilibrium. Scientists were stunned. Could this be a flaw in the data or something far more profound? Enter the void hypothesis. When light travels through a cosmic void, it loses energy climbing out of the void's gravitational well, a phenomenon called the integrated Sachs-Wolf effect. The result, the light shifts slightly toward the red end of the spectrum, cooling the cosmic microwave background in that direction. If the cold spot aligns with an underdense region of space, it could be the universe's way of casting a shadow. Some researchers point to the Boötes Supervoid, a candidate structure lurking in the cold spot's vicinity, as the possible culprit, but there's a problem. The Boötes Supervoid, while enormous, might not be large enough to explain the cold spot's extreme chill. Simulations suggest it would take a void far more vast or far emptier to produce such a stark temperature drop. This mismatch has led to a fiery debate in cosmology. One camp argues the cold spot is simply a rare statistical fluctuation, a cosmic roll of the dice that landed on an improbable outcome. Others propose wilder ideas. Could it be evidence of a collision with another universe, a relic of exotic physics, or even a flaw in our understanding of dark energy? The stakes couldn't be higher. If the cold spot is confirmed as a void imprint, it would validate key predictions of cosmology while pushing our models to their limits. But if no void can fully account for it, we might be staring at a crack in the standard model itself, a hint that the universe holds secrets we've yet to imagine. For now, telescopes like the Dark Energy Survey and the upcoming Euclid mission are scanning the cold spot's neighborhood, hunting for clues in the darkness. Whatever they find, one thing's clear: this frigid anomaly isn't just a curiosity, it's a cosmic detective story, and the final twist is still unwritten. To understand how void superclusters emerged from the chaos of the Big Bang, we have to zoom way in, to the universe's first fractions of a second. Picture a realm so hot and dense that matter and energy were interchangeable, a seething quantum soup where particles flickered in and out of existence. In this primordial inferno, tiny fluctuations in density arose purely by chance, regions where the soup was ever so slightly thicker or thinner. These weren't dramatic differences. Imagine a ripple on a pond smaller than an atom, but they held the seeds of everything to come. Fast forward 400,000 years, and the universe had cooled enough for atoms to form, releasing the afterglow we now call the cosmic microwave background. Embedded in that glow were the fingerprints of those early density variations, warmer spots where matter was slightly packed together, cooler spots where it was sparser. At the time, these differences were minuscule, less than 1 part in 100,000. But over billions of years, gravity would amplify them in a cosmic game of rich gartriture. The slightly denser regions pulled in more matter, growing even denser, while the sparser regions lost out, their matter slowly siphoned away. Here's where the magic happens. Those underdense patches didn't just stay small, they ballooned. As gravity pulled matter into filaments and clusters, the emptier regions stretched, their expansion fueled by dark energy's relentless push. Think of it like stretching a rubber sheet. The thin spots grow wider while the thick spots bunch together. By the time the universe was a few billion years old, what began as quantum whispers had become cosmic shouts, voids spanning hundreds of millions of light years. The real marvel is how predictable this process is. Run the equations backward from today's void superclusters, and they trace perfectly to those initial fluctuations. Simulations like the Bolshoi project, which model the universe's evolution from its first moments, recreate voids with startling accuracy simply by inputting the early density variations we see in the cosmic microwave background. It's like watching a time lapse of a growing forest where tiny seedlings inevitably become towering trees, except here, the seedlings are subatomic ripples and the trees are vast cosmic deserts. But there's a twist. Not all voids are created equal. Some, like the Boötes Void, grew unusually large, possibly because their initial underdensities were slightly more pronounced. Others, like the local void near our Milky Way, are more modest, their growth stunted by nearby superclusters' gravitational pull. This variation hints at something profound. The universe's structure isn't just shaped by randomness, but by an intricate interplay of chance and physical law. Those quantum fluctuations set the stage, but the exact script where voids would grow vast, where galaxies would cluster, was written by gravity, dark energy, and time. What's mind-bending is the scale of it all. Those first fluctuations were smaller than a proton, yet they dictated the distribution of matter across billions of light years. It's as if the universe played a game of connect the dots with impossibly tiny marks, and the resulting picture was the cosmic web we see today, and the void. They're not just blank spaces, they're the echoes of absence, the inverse imprint of where matter chose not to go. This isn't just a story about emptiness. It's a testament to how the universe transforms microscopic imperfection into macroscopic grandeur. The same physics that packed galaxies into superclusters also carved the voids between them, two sides of a coin stamped in the fiery forge of the Big Bang. So when we stare into these cosmic abysses, we're not just seeing nothing, we're seeing the aftermath of creation itself, frozen in the silent sprawl of space. Mapping the cosmic web isn't just about charting what's out there. It's a high-stakes test of our deepest cosmic theories. Projects like the Dark Energy Spectroscopic Instrument, or DESI, and the European Space Agency's Euclid telescope are revolutionizing this effort, turning the universe's voids and filaments into a laboratory for physics. Imagine these missions as cosmic cartographers, but instead of sketching coastlines, they're tracing the invisible scaffolding of reality itself. DESI, perched atop a mountain in Arizona, isn't your average telescope. Its 5,000 robotic eyes can simultaneously capture the light of millions of galaxies, measuring their precise distances with a technique called redshift surveys. By doing this, it's creating the most detailed three-dimensional map of the universe ever attempted, one that stretches back 11 billion years. But here's the twist: DESI isn't just looking at galaxies. It's studying the voids between them, measuring how their shapes and sizes align with predictions from Einstein's general relativity. When light from distant quasars passes through these voids, subtle distortions reveal the tug of dark matter and the push of dark energy, offering clues to why the universe's expansion is accelerating. Meanwhile, Euclid takes this hunt into space. Launched in 2023, this telescope avoids Earth's atmospheric blur to peer even deeper into the cosmic web. Its mission: to map the geometry of the universe with precision, focusing on how voids evolve over time. Euclid's infrared eyes can detect the faintest galaxies lurking in void walls, galaxies often missed by other surveys. By tracking how these structures grow and change, scientists hope to settle one of cosmology's biggest debates. Is dark energy constant, as Einstein's cosmological constant suggests, or does it vary across space and time? The data from these projects is already rewriting textbooks. In 2021, DESI preliminary maps revealed voids that were slightly larger and emptier than simulations predicted. Some researchers speculate this could hint at exotic physics, like dark energy growing stronger over time or even an undiscovered particle influencing cosmic expansion. Others caution it might be a statistical fluke, but the mere possibility has sent theorists scrambling back to their chalkboards. Euclid's first images, released in late 2023, added fuel to the fire. They showed void filaments with sharper edges than expected, as if some unseen force were shearing them into clean lines. What makes these surveys truly groundbreaking is how they turn emptiness into evidence. Voids, once dismissed as uninteresting blanks, are now critical benchmarks for testing gravity itself. Alternative theories like modified Newtonian dynamics or extra-dimensional models predict voids should grow and warp differently than in standard cosmology. KBC and Euclid can spot these discrepancies by measuring void shapes down to a fraction of a percent, a level of precision unimaginable a decade ago. But the real treasure lies ahead. Over the next decade, these missions will compile maps so detailed they'll function as cosmic time lapses, showing how voids have stretched and twisted since the universe's youth. Combined with data from upcoming projects like NAS and Nancy Grace Roman Space Telescope, we might soon have an answer to why voids exist in the sizes they do, and what that reveals about dark energy's true nature. For now, each new data release is like adding a piece to an infinite puzzle. The cosmic web isn't just structure, it's a story written in gravity, dark matter, and the relentless push of nothingness. And with every void mapped, we're decoding another line of that story, one that might end with the universe's ultimate fate. So while these surveys scan the darkness between galaxies, they're really illuminating something far grander, the hidden rules that govern everything. Void superclusters aren't just empty expanses, they're cosmic time capsules, preserving secrets about the universe's expansion in their vast, low-density chambers. Think of them as ancient amber, trapping bubbles of the past where the frenetic pace of cosmic evolution slowed to a crawl. While galaxy clusters churn with collisions and star formation, voids remain eerily serene, their sparse matter barely disturbed for billions of years. This stillness makes them pristine laboratories, offering a clearer signal of dark energy's influence than anywhere else in the cosmos. Here's why, in dense regions like superclusters, gravity's fierce tug complicates the picture, warping space-time in ways that mask dark energy's subtle effects. But in voids where matter's grip is weakest, dark energy's relentless push dominates unimpeded. It's like comparing a roaring river to a still pond. The river's currents hide tiny ripples while the pond reveals even the faintest breeze. By studying how voids expand over time, astronomers can measure dark energy's strength with unprecedented precision. The Sloan Digital Sky Survey revealed this in action, showing voids growing faster than expected, a smoking gun for dark energy's accelerating influence. But the real treasure lies in the echoes of the early universe. Voids preserve a fossil record of cosmic expansion because their growth is governed by the same density fluctuations that seeded all structure. The larger the void, the earlier it began forming, meaning gargantuan voids like Boötes are essentially snapshots of the universe's adolescence. Their shapes, sizes, and distributions encode information about the primordial forces that shaped them, untouched by the chaotic violence of galaxy formation. Some of the most tantalizing clues come from Baryon acoustic oscillations, sound waves frozen in time from the universe's first 380,000 years. These waves left a detectable imprint like cosmic ruler marks in the spacing between void walls. By measuring these patterns, projects like KBC can trace how dark energy stretched the universe's fabric at different epochs. The result, a timeline of cosmic expansion more detailed than anything gleaned from supernova or galaxy clusters alone. Yet voids harbor even deeper mysteries. Their underdense environments may host exotic phenomena impossible to study elsewhere. Some theories suggest quantum fluctuations in empty space, normally drowned out by matter's noise, could be amplified in voids, creating detectable anomalies. Others propose that voids might reveal cracks in Einstein's relativity, as their extreme low-density regions test gravity's laws in ways dense environments never could. What's certain is this: the universe's emptiest places are anything but barren. They're archives of cosmic history written in the language of absence. Every void's expanse, every faint galaxy drifting within it, tells a story, one that begins with the Big Bang and ends with the universe's fate. To study them is to read the universe's diary, penned in the negative space between the stars. Hidden in plain sight, wrapped around our galaxy like a cosmic cloak, lies the KBC Void, the largest known emptiness in the observable universe, and we're floating right inside it. Named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who identified it in 2013, this staggering void spans an almost incomprehensible 2 billion light-years across. That's right, the Milky Way isn't just near a void, it's nested in the heart of one, a fact that flips our cosmic perspective on its head. While most galaxies cluster along dense filaments, we're outliers, adrift in a bubble of near-nothingness so vast it could swallow 60,000 Milky Way side by side. What makes the KBC Void so unusual isn't just its size, it's how perfectly it upends expectations. Typical voids occupy about 85% of the universe's volume, but they're bordered by walls of galaxies. The KBC Void, though, is eerily self-contained. Instead of a hollow sphere, it's more like an onion with concentric shells of galaxies wrapping around its emptiness. Our local group of galaxies sits in one of these thin shells, like a dust speck clinging to the surface of a soap bubble. And outside this bubble, the universe gets denser, more crowded, meaning we're literally living in the middle of a cosmic backwater. But here's where it gets controversial. The KBC Void might hold the key to one of cosmology's biggest puzzles, the Hubble tension. For decades, astronomers have battled over conflicting measurements of the universe's expansion rate. Observations of nearby galaxies suggest a faster expansion, while the cosmic microwave background points to a slower one. This discrepancy has sparked crises in physics, with some even questioning Einstein's theories. Enter the KBC Void. If we're inside a giant underdense region, gravity's weaker pull here could be accelerating our local space-time relative to the denser universe outside. Think of it like a boat caught in a gentle current. We're moving faster because there's less resistance. Critics argue the void's sheer size stretches plausibility. The standard model of cosmology predicts voids no larger than 1.2 billion light-years, yet the KBC Void dwarfs that. Supporters counter that rare fluctuations could produce such a structure. After all, someone had to be in the biggest void. The debate hinges on precise measurements of galaxy distributions, with surveys like DAISY scrambling to map our neighborhood in unprecedented detail. If the KBC Void is real, the implications are staggering. It would mean we've been measuring the universe's expansion from inside a gravitational anomaly, skewing our cosmic yardsticks. Correcting for this could reconcile the Hubble tension without revising fundamental physics. But if it's disproven, the mystery deepens, forcing us to confront even more radical possibilities, perhaps new forces or dimensions influencing cosmic growth. Either way, the KBC Void forces a humbling realization. Our galactic home isn't just ordinary. It's perched on the edge of nothingness, a fluke in the cosmos' grand design. And that, ironically, makes it extraordinary. Imagine a galaxy so isolated that if you stood on one of its planets, the night sky would be almost pitch black. No neighboring galaxies close enough to see with the naked eye, no glittering cosmic companions. This isn't a thought experiment, it's the reality for MCG plus 01020015, nicknamed the loneliest galaxy. Drifting nearly 100 million light-years from its nearest galactic neighbor, this solitary spiral sits deep inside the void between superclusters, a cosmic castaway in an ocean of nothingness. Most galaxies live in bustling clusters or along dense filaments, But void galaxies like this one are the outliers, isolated survivors in a universe that favors crowds. What makes these loners so fascinating is how starkly they differ from their cluster-dwelling cousins. In crowded galactic neighborhoods, gravity's relentless tug distorts shapes, stripping away gas and triggering violent collisions. But void galaxies evolve in near-total isolation, untouched by the gravitational drama that shapes clusters. The result, they're often smaller, slower growing, and eerily pristine. Without nearby galaxies to disrupt them, they retain more of their primordial gas, the raw fuel for star formation. Some, like MCG plus 0102015, are even red and dead before their time. Their star formation quenched not by external forces, but by the sheer lack of new material to feed on. It's like a tree stranded in a desert, stunted not by competition, but by emptiness. Yet void galaxies aren't just passive relics. Their solitude makes them ideal laboratories for studying galactic evolution in its purest form. Take UGC 3672, another void dweller. Unlike cluster galaxies, which often grow by cannibalizing their neighbors, this one has spent billions of years forming stars at a slow, steady pace. Its spiral arms are symmetrical and undisturbed, a testament to the quiet existence void galaxies enjoy. Even their dark matter halos differ, less compact and more diffuse, reflecting the gentler gravitational environment of voids. The loneliest galaxies also hold clues to one of astronomy's biggest puzzles: why some voids aren't entirely empty. Theories suggest these isolated systems might be backsplash galaxies, ejected from clusters long ago during violent encounters. Others could be primordial holdouts, rare overdensities that somehow survived the void's expansion. Then there's the tantalizing possibility that dark matter's subtle clumping left behind faint trails of gas, allowing these galaxies to form against all odds. But the real surprise, some void galaxies defy expectations by thriving. Despite their isolation, a rare few, like the blue compact dwarf galaxy SDSS 0335-052, are stellar factories churning out new stars at rates that rival bustling cluster galaxies. The secret may lie in their undisturbed gas reserves without competition or collisions. They can hoard fuel for billions of years, igniting sudden bursts of star formation when conditions align. It's a reminder that even in the universe's emptiest realms, life finds a way. Studying these cosmic hermits isn't easy. Their faintness makes them elusive, often hidden in the glare of foreground stars. But telescopes like Hubble and the forthcoming Nancy Grace Roman Space Telescope are changing the game, peering deeper into voids than ever before. Each discovery rewrites our understanding of how galaxies evolve, proving that the universe's loneliest places aren't just barren, they're frontiers of the unknown. So the next time you gaze at the night sky, remember, for every glittering cluster, there's a galaxy out there floating in perfect solitude, a silent witness to the cosmos' quietest corners. What if the vast, empty stretches of void superclusters aren't just cosmic accidents but fingerprints of other universes? It's a radical idea, one that dances on the edge of established physics, yet some scientists speculate these voids could be scars from collisions with bubble universes in a hidden multiverse. Picture our universe as one soap bubble in an infinite foam, where neighboring bubbles occasionally brush against each other. When they do, the gravitational tug of war might leave behind voids, immense, asymmetrical absences where matter was pushed aside. The KBC Void, with its puzzling scale and onion-like structure, has even been proposed as a candidate for such an imprint, a cosmic bruise from a long-ago encounter with another reality. The math behind this isn't pure fantasy. In certain multiverse models, like eternal inflation, new universes constantly bud off from a quantum foam, each with its own physics. When two bubbles collide, the energy released could warp space-time, creating underdense regions. Simulations by theorists like Laura Mersini-Horton suggest these collisions might leave distinct patterns in the cosmic microwave background, patterns some argue align with anomalies like the cold spot. If true, voids wouldn't just be empty space, they'd be archaeological sites preserving evidence of universes beyond our own. Critics, of course, point out the lack of smoking gun evidence. The cold spot could still be a statistical fluke, and the KBC void might just be a rare overreach of cosmic inflation. But the mere possibility forces us to confront a profound question. If voids are multiverse artifacts, how would we even confirm it? One clue might lie in their shapes. Bubble collision voids would likely be lopsided with uneven edges, unlike the smoother voids formed by dark energy alone. Surveys like Euclid are now mapping void geometries with unprecedented precision, hunting for these telltale asymmetries. Another hint could come from gravity's behavior. In some multiverse models, the collision zone might warp spacetime differently than standard physics predicts, subtly altering how light bends around voids. Telescopes like DAISY and the Vera Rubin Observatory are scanning for these deviations, testing whether void lensing matches Einstein's predictions or hints at something stranger. Yet the wildest twist isn't the science, it's the philosophical implications. If voids are shadows of other universes, then the cosmos isn't just expanding, it's breathing, brushing against realities where the laws of physics might be unrecognizable. Empty space, long dismissed as mere backdrop, could be the most active frontier of all, a window into dimensions beyond our own. For now, it's a hypothesis dancing at the edge of proof. But in a universe where emptiness shapes everything, even the gaps might be trying to tell us something. To understand how void superclusters sprang from the quantum chaos of the early universe, picture a pot of water just before it boils, a seething dance of tiny bubbles forming and popping at random. Now shrink that image down to subatomic scales, where the newborn universe was 1 trillion times hotter than the sun's core, and those bubbles weren't made of water vapor but of raw spacetime itself. In that primordial fury, quantum fluctuations, brief, unpredictable changes in energy created microscopic ripples in the density of matter. Most vanished instantly, but a few were stretched to cosmic proportions by inflation, that explosive expansion of space in the universe's first fraction of a second. These surviving ripples became the seeds of everything, from glittering galaxy clusters to the vast voids between them. Here's where the magic happens. Imagine blowing up a balloon with an uneven rubber thickness. The thinner spots stretch easiest, becoming larger and more pronounced as the balloon inflates. That's exactly how underdense regions in the infant universe behaved. Areas with slightly less matter expanded faster, their weaker gravitational pull allowing space itself to stretch more readily. Over billions of years, these patches grew into the voids we see today, while the denser regions collapsed into galaxies. The kicker, the initial density differences were ridiculously small, about 1 part in 100,000. That's like detecting a single grain of sand missing from a beach and having that tiny deficit eventually carve out the Grand Canyon. The foam bubble analogy works even deeper. Just as soap suds cluster into interconnected empty spheres, the universe's voids form a similar cosmic web, with galaxies tracing the delicate walls between them. But here's the twist: quantum foam isn't just a metaphor. At Planck scales, 1 billion trillion times smaller than an atom, space itself may froth with fleeting bubbles of energy popping in and out of existence. Some theorists suggest these quantum bubbles could have left imprints on the early universe's density fluctuations, meaning the voids we see today might literally be quantum physics writ large across the cosmos. Evidence for this lies in the cosmic microwave background, the afterglow of the Big Bang. Those faint temperature variations, slightly cooler spots where matter was sparser, align perfectly with today's void locations. It's as if the universe left us a blueprint showing how microscopic quantum jitters were amplified into cosmic emptiness. Simulations like those from the Illustris TNG project confirm this, tracing void formation from initial quantum ripples to the present-day web of galaxies and voids. Run the simulation backward, and the voids shrink seamlessly back to those original fluctuations, like rewinding a film of an inflating balloon, yet mysteries linger. Why did some fluctuations grow into voids hundreds of millions of light-years wide, while others remained modest? The answer might lie in dark energy's accelerating push, which preferentially stretches underdense regions. Or perhaps certain quantum fluctuations were simply luckier, their random positions allowing them to grow unchecked. What's certain is that without those initial quantum whispers, the universe would look utterly different. A bland, uniform sea of matter with no voids, no galaxies, and likely no us. So next time you gaze at the night sky's darkness between stars, remember, you're not just looking at empty space. You're seeing quantum mechanics played out on the grandest scale, a frozen echo of the universe's fiery birth where nothingness shapes everything. Void superclusters have long captivated not just scientists, but storytellers too, transforming these cosmic deserts into backdrops for humanity's most imaginative tales. Take Frank Herbert's Dune, where the concept of the void isn't just empty space, but a psychological frontier. The Bene Gesserit's fear of falling into the void mirrors our own dread of insignificance in the face of cosmic emptiness. Herbert's genius was in turning astrophysical reality into metaphor. The void isn't just a place, but a reflection of the unknown, an abyss that challenges explorers and empires alike. Then there's Interstellar, where the Tesseract sequence bends the laws of physics inside a higher dimensional void. Nolan's depiction isn't pure fantasy. It echoes real theories about quantum foam and brain cosmology, where voids could harbor alternate dimensions. The film's portrayal of time as a physical dimension within the void structure isn't far from scientific speculation. Some models suggest dark energy's influence could warp spacetime similarly in real-life cosmic voids. The Tesseract's labyrinthine bookshelves, a poetic nod to how voids might archive the universe's history, light from billions of years frozen in their expanse. Sci-fi often exaggerates voids as hazards like Warhammer 40K's warp, a chaotic subspace where physics breaks down, but the inspiration isn't baseless. Real voids do distort reality. Their gravitational pull can lens light, stretch time, and even slow cosmic expansion locally. Games like Elite Dangerous take this further, rendering voids as navigational nightmares where stars are scarce and hyperspace jumps risk stranding players in the abyss. It's a gameplay mechanic rooted in real astrophysics without dense matter to calibrate against. Traversing voids would be perilous. What these stories grasp is the void's duality. It's both a prison and a portal. Stargate Universe explored this by stranding its crew in a void between galaxies, turning isolation into existential drama. Meanwhile, the Three-Body Problem trilogy imagines voids as cosmic minefields where civilizations hide to avoid annihilation. Liu Cixin's Dark Forest theory that voids might harbor stealthy predators plays on humanity's oldest fear, the monsters lurking in the unknown, the thread connecting these tales. Voids aren't just settings, they're characters. Their emptiness becomes a canvas for existential questions. What happens when we're untethered from everything familiar? Can life persist where the universe seems to give up? Sci-fi's answer is a resounding yes, but with a twist. Whether it's Doctor Who's void ships or Star Trek's void dwellers, fiction suggests that where science sees absence, imagination sees possibility. Perhaps that's why voids haunt our stories. They're the ultimate blank slate, not just spaces between stars, but between ideas. Every sci-fi void, no matter how fantastical, whispers a truth. The universe's emptiest places are where we project our boldest dreams and darkest fears. And sometimes, in that tension between science and speculation, we catch glimpses of tomorrow's discoveries. Could life emerge in the crushing isolation of a cosmic void? At first glance, the idea seems absurd. These vast deserts span hundreds of millions of light years with barely a handful of galaxies, let alone hospitable planets. But the universe thrives on defying expectations. Take the rare void galaxies like MCG plus 0102015 drifting alone in the abyss. Unlike their crowded counterparts, these isolated islands evolve under wildly different rules. With minimal gravitational disturbances, they often retain ancient stocks of pristine gas, the raw material for star formation. Some even experience sporadic bursts of stellar birth, igniting brief eras of warmth in an otherwise frigid expanse. The question isn't just whether life could exist here, it's whether void galaxies might offer unexpected advantages over the chaos of galactic clusters. Radiation levels tell a surprising story. In dense galaxy clusters, frequent supernova and active galactic nuclei bombard nearby systems with lethal gamma rays and cosmic rays. But in the quiet of a void, radiation exposure could be far lower. Without neighboring stars going supernova every few millennia, void planets might enjoy calmer space weather, less atmospheric stripping, fewer mass extinctions. Earth's own history shows how critical this stability is. Our planet's long periods of relative calm allowed complex life to flourish. A void world, sheltered by its isolation, could theoretically offer even longer stretches of uninterrupted evolution. Yet the challenges are staggering. Void galaxies suffer from a crippling shortage of heavy elements, the iron, silicon, and carbon essential for rocky planets and organic chemistry. These elements are forged in stellar explosions and spread through galactic collisions, both rarities in the void. A void planet might orbit a star so metal-poor that its very crust lacks the minerals needed for tectonic activity or oceans. Even water could be scarce, as icy comets, often delivered by gravitational nudges from passing stars, would have few opportunities to bombard fledgling worlds in these empty quarters. Then there's the problem of energy. With fewer stars forming, void galaxies emit less ambient light. A hypothetical void planet might orbit a dim red dwarf, its skies perpetually twilight. Photosynthetic life would struggle, forcing ecosystems to rely on chemosynthesis or other exotic energy sources. Some astrobiologists speculate that life in such conditions could evolve to harness energy from cosmic rays or tidal forces, processes far removed from Earth-Sun-dependent biology. But the most tantalizing possibility lies in timing. Void galaxies evolve slowly, their stellar populations aging at a leisurely pace compared to the frenetic star formation in dense clusters. This delayed development could extend the window for life's emergence. While cluster galaxies might burn through their resources in a few billion years, void galaxies could remain fertile for tens of billions, offering life a vastly longer runway to arise. Imagine a civilization blooming in the void's quietude, its astronomers peering into a night sky almost devoid of neighboring stars, their isolation both a curse and a blessing. The debate isn't settled. Some researchers argue void galaxies are simply too impoverished to host life, while others see them as dark horses, places where isolation fosters resilience. Future telescopes like the James Webb Space Telescope could tip the scales, analyzing the atmospheres of void exoplanets for biosignatures. Until then, the voids remain cosmic question marks, their emptiness whispering possibilities we're only beginning to fathom. As dark energy tightens its grip on the cosmos, void superclusters are poised to become the universe's ultimate rulers, expanding faster and growing emptier with every passing eon. Picture a future so distant that the galaxies we see today are mere ghosts, their light stretched beyond detection, and the voids between them swollen to incomprehensible scales. This isn't science fiction, it's the inevitable fate of a universe where dark energy calls the shots. Current models suggest that in about 100 billion years, the Milky Way and its nearest neighbors will be the only visible objects in our sky, huddled together in an isolated pocket while the voids around us stretch into infinity. The rest of the cosmic web faded into darkness, its galaxies pushed beyond the horizon of observation by the accelerating expansion of space. But the real transformation happens deeper into the future. As voids grow, they'll begin to merge, their boundaries dissolving like soap bubbles combining into ever larger cavities. The local void near our galaxy might one day fuse with giants like Boötes, creating voids spanning billions of light years, so vast that even their namesakes would seem tiny by comparison. Inside these megavoid superstructures, the few remaining galaxies will experience a paradox. While the universe as a whole expands faster, their local neighborhood will contract. Gravity's pull will bind them into tight clusters, floating like lonely islands in an ever-widening sea of nothingness. The physics of this era defies intuition. As voids dominate, they'll warp the very fabric of reality. Light traveling through them will redshift so dramatically that even the most energetic gamma rays will stretch into feeble radio waves. Time itself will appear to slow near these cosmic deserts, as the lack of mass weakens gravity's influence on space-time. Civilizations born in this epoch, if any survive, would witness a sky unlike anything we know. Their telescopes would reveal no distant galaxies, no cosmic microwave background, just an impenetrable blackness punctuated by a handful of nearby stars. The universe's history, written in light, would be lost to the void's expansion, leaving future astronomers with no clues to the Big Bang or the vibrant cosmic web we see today. Yet the void's triumph won't last forever. Some theories suggest that in a trillion years, quantum tunneling could ignite new Big Bangs within these empty regions, random fluctuations birthing fresh universes in the void's depths. Others propose that dark energy might decay, allowing gravity to reassert control and collapse the voids back into a cosmic crunch. For now, these ideas remain speculative, but they hint at a profound truth. Void superclusters aren't just the end game of our universe's story. They might also be the beginning of another. What's certain is this: the voids we see today are time machines offering glimpses of a future where emptiness is the cosmos' defining feature. They remind us that the universe is never static. It's a dynamic, evolving entity where even the absence of matter shapes destiny. So when we peer into these abysses, we're not just studying space. We're reading the universe's last will and testament, written in the slow, relentless expansion of nothingness. The relentless expansion of void superclusters isn't just reshaping the cosmos, it's rewriting its ultimate fate. One of the most chilling possibilities is the Big Rip, a scenario where dark energy's accelerating push becomes so powerful that it doesn't just stretch space but shreds it. Imagine the universe's fabric stretched taut until galaxies, stars, and even atoms are torn apart in a final, catastrophic moment. Voids, as the fastest-growing structures in the universe, might be the early warning signs of this cosmic apocalypse. Their unchecked expansion could be the preview of a far more violent finale, where the very bonds holding reality together snap. Right now, dark energy's grip is subtle but unrelenting. As voids grow, they're not just passively stretching, they're actively accelerating the universe's disintegration. The math behind this is as elegant as it is terrifying. In most models, dark energy's strength is represented by a W parameter. If this value dips below -1, the universe enters phantom energy territory, a state where dark energy's density increases over time, amplifying its destructive potential. Voids with their negligible matter content become the testing grounds for this phenomenon. Their expansion rates, measured by projects like DAISY, already show hints of acceleration beyond standard predictions. If this trend continues, it could signal that dark energy isn't just constant but growing stronger, inching us toward the Big Rip's inevitability. But the Big Rip isn't the only fate tied to voids. Some cosmologists propose a gentler but equally eerie alternative: heat death. In this scenario, voids keep expanding until they dominate the cosmos, but space itself never ruptures. Instead, galaxies become isolated islands, their stars burning out one by one until the universe fades into a lifeless, ultra-cold equilibrium. The voids would win not through violence but through sheer, relentless dilution, a slow-motion erasure of all structure. The difference between these two outcomes hinges on dark energy's exact behavior, and voids are the universe's way of broadcasting which path we're on. The most unsettling part, we might already be living in the early stages of this cosmic unraveling. Simulations show that in a Big Rip scenario, the first structures to go would be galaxy clusters torn apart by dark energy's mounting pressure. Next, individual galaxies would disintegrate as their stars are flung into the void. Finally, in the last moments, even atomic nuclei would be ripped asunder. The timeline for this is staggeringly distant tens of billions of years, but the process could already be underway, with voids as the harbingers. Yet there's a twist. Voids might also hold the key to averting this fate. Some theories suggest that if dark energy's strength fluctuates, voids could act as cosmic dampeners, their low-density environments subtly resisting acceleration. Others speculate that quantum phenomena within voids might birth new physics, offering escape routes we haven't yet imagined. It's a cosmic irony. The very structures speeding us toward destruction could also hide the tools for salvation. For now, the truth lies in the data. Every void mapped, every expansion rate measured, brings us closer to knowing whether our universe will end with a bang, a rip, or a whisper. And as these cosmic deserts grow, they're not just empty space, they're the universe's final message, written in the slow-motion collapse of everything we know. Peering into the cosmic voids isn't like staring at a star cluster or galaxy. These immense absences resist observation, hiding in plain sight. To map nothingness, astronomers employ some of the most ingenious tools in science, transforming the void's very emptiness into a lens for discovery. Take radio telescopes like ALMA in Chile's Atacama Desert. While optical telescopes struggle to spot the faint galaxies drifting in voids, ALMA dishes detect the cold hydrogen gas between them, tracing invisible threads of matter that outline the void's skeleton. It's akin to studying a silhouette instead of the object itself. The void's shape emerges from what little clings to its edges. But the real game changer has been gravitational lensing. When light from a distant quasar passes through a void, the void's weak gravitational field subtly bends the light's path, distorting the quasar's image like a funhouse mirror. By measuring these distortions, instruments like the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope can map the void's mass distribution, including its elusive dark matter. The irony, the less a void contains, the more it reveals. These empty regions act as cosmic scales, weighing the universe's missing mass through the very absence of stuff. Yet the challenges are staggering. Void galaxies are often dwarfed by their cluster counterparts, their light drowned in noise. To compensate, projects like the Sloan Digital Sky Survey deploy fiber optic spectrographs that can capture thousands of galaxy spectra simultaneously, sifting void dwellers from the cosmic crowd. Even then, voids demand patience. Their signals are so faint that observations might take months, piecing together glimpses like a jigsaw puzzle where most pieces are missing. The latest frontier, 21-centimeter radio astronomy, which hunts the faint glow of neutral hydrogen from the universe's infancy. Experiments like HERA and the SKA Observatory aim to detect how early voids shape the cosmic web, using wavelengths that pierce dust clouds obscuring optical views. It's a reminder that to study voids, we must embrace the unconventional, because in the universe's quietest places, the answers aren't written in light but in the whispers between. One of the biggest myths about void superclusters is that they're completely empty, just endless black nothingness with absolutely nothing inside. In reality, these cosmic deserts are more like sprawling ghost towns than pure vacuums. While they contain far fewer galaxies than denser regions, traces of matter still linger. Rogue galaxies drift through them like solitary travelers, many stripped of star-forming gas but still glowing faintly with ancient stars. Even the space between these lonely galaxies isn't truly empty. Thin clouds of hydrogen gas left over from the universe's earliest days stretch across the voids, and dark matter, though sparser than in galactic filaments, still weaves through them like an invisible net. Calling a void empty is like calling the Sahara barren because it lacks cities, ignoring the grains of sand, the occasional oasis, and the life that adapts to the harsh conditions. Another common misconception is that voids are just giant black holes, cosmic vacuum cleaners sucking everything into oblivion. Black holes warp space-time with crushing gravity, pulling matter inward past a point of no return. Voids, on the other hand, are defined by the lack of gravitational pull. Their emptiness isn't due to destruction but to expansion. Think of the difference between a whirlpool dragging objects under a black hole and a calm lake where no boats ever drift a void. The galaxies at a void's edges aren't being consumed, they're being pushed outward by dark energy's relentless force, like leaves scattered by an invisible wind. Then there's the myth that voids are cold, frozen wastelands. While it's true they lack the heat of countless stars, their temperature is more nuanced. The cosmic microwave background, the afterglow of the Big Bang, actually appears slightly warmer in voids when observed from Earth. Here's why: as light travels through a void, it loses energy climbing out of the void's shallow gravitational well, a process called the integrated Sachs-Wolf effect. This makes the light appear cooler, but the void itself isn't cold. In fact, the sparse gas within a void can be hotter than expected, heated by shocks from rare galactic collisions or energy from dark matter interactions. Some even believe voids are dangerous, that entering one would doom a spaceship to eternal isolation. While navigating a void would certainly pose challenges, the real danger isn't the void itself but the lack of resources. With stars so far apart, a vessel might struggle to refuel or slingshot around gravity wells. Yet mathematically, a straight path through a void could be safer than weaving through crowded galactic clusters where black holes, supernova, and gamma-ray bursts lurk. Voids are less a cosmic death trap and more a marathon of emptiness requiring patience and planning, but not certain doom. Perhaps the most persistent myth is that voids are static, unchanging expanses. Nothing could be further from the truth. These regions are dynamic, growing larger as dark energy accelerates their expansion. Galaxies near void edges are slowly pulled away by this expansion, like boats drifting from shore on an outgoing tide. Meanwhile, simulations suggest some voids might eventually merge, creating megavoid structures that redefine cosmic geography. Far from being frozen snapshots, void superclusters are active participants in the universe's evolution, their emptiness shaping the fate of everything around them. Dispelling these myths isn't just about accuracy, it's about appreciating voids for what they truly are. They're not cosmic errors or gaps in the universe's design. They're fundamental to its structure, as essential as the galaxies themselves. The more we understand their nuances, the more we see the universe not as a collection of bright objects surrounded by nothing, but as an intricate dance between presence and absence where both play equally vital roles. Could advanced civilizations harness the vast emptiness of void superclusters as cosmic shortcuts or energy reservoirs? The idea isn't as far-fetched as it sounds. With their minimal matter density and near absence of gravitational interference, these cosmic deserts might be the universe's ultimate express lanes for theoretical faster-than-light travel. Imagine a hypothetical hyperdrive technology that warps space-time, a concept like the Alcubierre drive, which compresses space ahead of a vessel while expanding it behind. In dense galactic regions, the sheer gravitational noise from stars and dark matter could destabilize such a warp bubble, but in a void, the smooth, uncluttered space-time might allow stable traversal, turning these empty expanses into interstellar superhighways for civilizations bold enough to navigate them. Energy harvesting is another tantalizing possibility. Voids might seem barren, but their very emptiness could be a resource. One radical theory suggests that advanced beings might tap into quantum fluctuations, the temporary particles that pop in and out of existence even in a vacuum. These fluctuations, amplified across the void's vast scale, could theoretically be harnessed via megastructures like Dyson swarms or vacuum energy extractors. The mechanics are speculative, but the principle echoes our own pursuit of zero-point energy, an unfathomable power source lurking in empty space. A civilization capable of such engineering wouldn't just survive in the void, they'd thrive, transforming its nothingness into an engine. Then there's the strategic advantage. In a universe where hostile civilizations might lurk in dense galactic clusters, voids could offer sanctuary or stealth. The absence of stars means fewer prying eyes, making voids ideal for hiding megastructures or entire Dyson spheres. Sci-fi often depicts voids as dead zones, but they might instead be the cosmic equivalent of a hidden fortress, where a civilization could operate undetected for eons. The Great Silence, the puzzling lack of detectable alien signals, might not mean we're alone. It could mean everyone else is hiding in the voids, communicating via channels we haven't yet imagined. But the most mind-bending idea, voids as cosmic archives, a Type 3 civilization, one that commands energy on a galactic scale, might use these regions to store information in unimaginable ways. Encoding data in the spin of rogue black holes or the polarization of cosmic microwave background radiation could turn voids into the ultimate hard drives, their emptiness guaranteeing stability over billions of years. A void's silence wouldn't be absence, it'd be a library, its contents invisible to those without the key. Of course, all this hinges on physics we've barely glimpsed. Yet the void's unique properties make them irresistible to theorists. Whether as highways, power plants, or sanctuaries, these cosmic deserts challenge our assumptions about life's limits. If intelligence arises in the universe's busiest neighborhoods, perhaps its greatest achievements unfold in the quietest. After all, darkness isn't the absence of light, it's the canvas for what comes next. Now, let's step into the void, not metaphorically, but as if we're piloting a starship through one of these cosmic deserts ourselves. Picture firing up a tool like Space Engine, a universe simulator that lets you traverse the cosmos from your screen. As you zoom out from Earth, past the familiar swirl of the Milky Way, the local group, and even the Laniakea supercluster, the galaxies begin to thin. Soon, you're staring into the abyss, the KBC Void, a yawning expanse where the nearest galaxy is so distant, it feels like you're floating in an endless obsidian sea. With a few clicks, you can toggle scientific overlays, revealing the void's structure in vivid detail. The edges glow faintly with filamentary threads, galaxies strung like pearls on invisible strings, marking the void's boundaries. Panning deeper into the emptiness, you notice a lone spiral galaxy, MCG plus 01020015, one of the rare void dwellers. Zooming in, its delicate arms appear undisturbed, lacking the warped shapes of galaxies in crowded clusters. This isolation isn't just aesthetic, it's a clue to how void galaxies evolve differently, their star formation slower, their gas reservoirs pristine. Switch to redshift mode, and the void's true scale snaps into focus. The galaxies at its edges appear redder, their light stretched by the void's expansion, a visual demonstration of dark energy's relentless push. Now engage the gravity lensing filter. Distant quasars behind the void appear slightly distorted, their images warped by the void's subtle gravitational field. This isn't just a cool effect, it's how real astronomers map dark matter's faint fingerprints in these regions. For a more immersive experience, try NASA's Eyes on the Universe or the Gaia Sky project. These tools let you fly through real observational data, like the Sloan Digital Sky Survey's Void Catalog. Track the paths of rogue galaxies drifting through the Boötes Void, or measure the growing gaps between filamentary walls over billions of simulated years. Notice how voids aren't static, they pulse and expand, their boundaries shifting like slow-motion tidal waves. Hands-on exploration changes everything. What seems abstract in a textbook terms like integrated Sachs-Wolf effect or Barrian acoustic oscillations becomes visceral when you watch light bend around a void's edges or hear the simulator's ambient hum drop to silence as you enter the emptiest regions. It's one thing to hear that voids make up 80% of the universe's volume. It's another to feel that scale as you navigate trillions of cubic light years with no destination in sight. So go ahead, download one of these apps, mute the lights, and lose yourself in the void. There's no better way to grasp the universe's grand design than by confronting its emptiness firsthand. Just don't be surprised if you come back with a newfound awe for the darkness between the stars and the eerie beauty of the places where almost nothing is. From the quantum ripples of the Big Bang to the accelerating silence of dark energy, void superclusters are more than just cosmic oddities, they're the universe's hidden architects. These vast deserts of emptiness, stretching hundreds of millions of light years, aren't passive blanks on the cosmic map. They're dynamic forces sculpting the fate of galaxies, testing the laws of physics, and even holding clues to realities beyond our own. Whether it's the Boötes Void's puzzling isolation, the KBC Void's unsettling scale, or the Cold Spot's cryptic chill, these absences challenge us to rethink everything we know about space, time, and our place in the grand scheme. But here's the humbling truth. In a cosmos where voids dominate 80% of the volume, the glittering galaxies we cling to are the exception, not the rule. We're fleeting sparks in an ocean of darkness, our existence framed by unimaginable emptiness. Yet there's beauty in that perspective. Every time we peer into these voids, we're not just staring at nothing, we're glimpsing the universe's deepest rhythms, the silent dance between presence and absence that's been unfolding for 13.8 billion years. So the next time you look up at the night sky, remember, the stars are just the prologue. The real story is written in the darkness between them, in the voids that stretch beyond comprehension, shaping the cosmos in ways we're only beginning to understand. If this journey through the universe's emptiest places left you awestruck, hit like and subscribe because the cosmos has infinite mysteries left to explore and we're just getting started. Until next time, keep looking up and wondering what lies beyond the void.